Hello class and welcome back to Advanced Functions. Today should be our last lesson on chapter 1, which would conclude polynomial functions. So let's get started. So chapter 1.5 would be covering slopes of secants and average rate of change. Of course, we'll be covering the rate of change itself, as well as average rate of change. I don't know if you've seen this. However, in chapter 1.6, we're also going to be covering instantaneous rate of change. So let's just get it over with what rate of change actually means. So a rate of change is a measure of how quickly one quantity, which would be the dependent variable, changes with respect to another quantity, which would be the independent variable. There are two types of rate of change: average and instantaneous. An average rate of change, or AROC as I will be referring to it, is a change that takes place over an interval, while an instantaneous rate of change, which is IROC, is a change that takes place in an instant. You should have already learned about some rates of change, for example, velocity and acceleration in grade 11 physics if you ever took that, so hopefully you're a little bit familiar with this concept. So let's first of all do average rate of change. First of all, it represents the rate of change over a specified interval, as stated before, and it corresponds to the slope of a secant between 2 points, P1 and P2 on a curve. A secant is essentially a line that intersects a curve within 2 points. The average rate of change is written as the change in y over the change of x, or delta y over delta x. And again, delta y over delta x could also be written as y2 minus y1 divided by x2 minus x1. Lastly, an average rate of change can be determined by calculating the slope between the 2 points in a given table of values, or by using an equation. So let's look at the following example. Using the following information, find the average rate of change of the population of an ant colony from the year 2007 to 2010. So as we have here, we have a table that shows the year and the population for a couple of the years. All we know is that we have to find the average rate of change, which would be over an interval. So the two intervals that we're concerned about are 2007 and 2010. And the way we find what the average rate of change is of course by applying delta y over delta x, which would mean we would have the first y value, or I guess the second y value as we refer to here, minus the first one, which this one, all divided by 2010 minus 2007. Of course, you could just quickly do this on your calculator, so I don't think we'll spend any more time on this. Now let's discuss instantaneous rate of change. An instantaneous rate of change tells you how fast y is changing with respect to x at any value of x. This may sound confusing, but just think of it as what happens at that specific point. How does the y value behave? An instantaneous rate of change is the slope of the tangent to a curve, which means that that line only touches the curve at one point. So this is what you do to find instantaneous rate of change, or IROC. First of all, you could use a graph. You could either estimate the slope of a secant passing through the point, or by sketching the tangent and estimating slope between the tangent point and the second point on the approximate tangent line. Then you could also use a table of values by estimating the slope between the point and a nearby point on the table. And lastly, you could use an equation by estimating the slope using a very short interval between the tangent point and a second point using the equation. So essentially what you're doing is you are following the same procedure as AROC, because we haven't gotten into calculus yet and we cannot find limits. However, this is what you have to do in this course. You will have to use a very small interval, or a very small number, difference between your first x value and your second x value. And with that in mind, you'll have to calculate the second y value and then find the rate of change. So for example, if you had to find IROC at x5, x equals 5, you'd use x1 is equals to 5, and x2 could be a number like 5.001 or 4.999, because those are extremely similar to how 5 is behaving. Okay, so this will be the last homework you'll get for this chapter. It will be combining chapter 1.5 and 1.6. I probably should have wrote the numbers, the page numbers, but I didn't, so that's what they mean. Of course, I will be going over each of these questions in the next portion of the video, so please stay tuned. Okay, so let's start with chapter 1.5, question 2. Identify if the average rate of change for the pairs of points along each graph is constant and positive, constant and negative, 0, or non-constant. Justify your response. Okay, so for A, we see that it is increasing as the x values increase, the distance increases, so it is positive. It also is constant because we have a straight line. Then for B, we see that it is a horizontal line, so its slope is 0, therefore the answer would be 0. Lastly, we have C, which is a downward slanted straight line, which would mean it is constant and negative. Okay, now let's move on to question 3. Determine the average rate of change for 2 points on each line segment for question 2. So let's just choose the points that seem the closest, or like the easiest to estimate. For example, we have the point 0, 1, and then the point 5, 8. So with that, we know it's delta y over delta x. So what we do is 8 minus 1 divided by 5 minus 0, which is 7 over 5, which would be our AROC value. Now for B, as we said, the slope of the line is 0, so we know that the y values are always the same, therefore your numerator would always be 0, therefore the AROC value would always be 0. Lastly, for C, immediately we could use the point 0.6, and then another good point would be 7.2. So then again we would do personally I don't like dealing with, well, actually we have to use negatives anyway, so we have 6 minus 2, that's how I do it, and 0 minus 7, which should be negative 4 over 7. And that is our AROC value once again. Now let's move on to question 5. The table shows the percent of Canadian households that used email from 1999 to 2003. Determine the average rate of change of the percent of households using email from 1999 to 2003. What are the units for this average rate of change? Okay, well, again, the only formula we know so far is delta y over delta x. So what we would do is we would use the values from 1999, which is 26.5, and 2003, 52.1. So B would just take 52.1 minus 26.3, all divided by 2003 minus 1999, and we would get our average rate of change. Then what the units are would be, of course, our percentage per year, because that's the units we have been using. Then now let's move on to question B. Why might someone want to know the average rate of change found in part A? Well, for example, I know we live in the age of the internet nowadays, but before it was an unknown circumstance for whether or not somebody would be transferring over to email or ever starting to use it. So it was like dwelling into the unknown. So it was very beneficial to know whether or not the platform is actually growing for demand or if it's gonna go into a stalemate and then never be used again. C. Determine the average rate of change for the percent of households using email for each pair of consecutive years from 1999 to 2003. Well, I'd rather you do this. However, I'll just do one simple example that shouldn't take long. I'll do like 3 of them and then you'll continue with the other ones. Okay, so for the first year of differences, we would have the year 2000. Come on. No. 2000 to 1999. The reason why I wrote this is because we shouldn't get negative numbers, so it makes more sense. So the values you would have is 37.4 minus 26.3 all over 2000 minus that, so which is 1, which is equals to approximately 11.1. Then we would have our next year, which is 46.1 minus 37.4 all over 2001 minus 2000, and that's equals to approximately 8.7. Next year we have 48.9 minus 46.1, again over 1, because you know each year we just differ by 1, it's approximately 2.8. Interesting. And then we have our last one, which is 52.1 minus 48.9 all over 1, which is approximately 3.2. The reason why I'm putting approximately is because I'm guessing these numbers are rounded, but you don't really have to do that. You could use the exact numbers. So honestly, I don't actually know. Let's get rid of them. Yeah, I started doing sound effects, so that's why I make those weird noises. Again, did it ask us to find the units? Sorry. Nope. But those are the numbers, and again, it will be percentage per year. Part D. Compare the values found in Part C. Which value is the greatest and the least? What are the significance of these values? Well, as we could see, the greatest one is the first one, which was 11.1. Then we had the least one is 2.8. And essentially, what it means is just this is the year where people started to genuinely become interested in email and a lot of people started using it, while over here we were just like, yeah, we're gonna use it but not that much, so it was the smallest increase we had. What's next? Compare the values found in Part A with those found in Part C. Explain any similarities or differences. Okay, well, in Part A, I don't think I actually wrote that down, so let me do that quickly. Part A. And we had 2052.1 minus 26.3 over. That was the worst line I've done. Over 2003 minus 1999, which is equal to 6.5. 4.5. Okay, so that's what we had here. Next, I would personally, by just looking at the graph and what the question is asking, I'm guessing it is the average of the four, because if it's average rate of change, and then we have 4 different averages for every year, if we combine all 4 of them to find the difference in the 4 years, I feel like that would make sense. So I'll just quickly see if that's the case. add them up and divide. Plus. Yep, that's exactly the case. So this is the average of all of those numbers. So that's cool. Now let's move on to question 7. Question 7. We have, as a large snowball melts, its size changes. This volume, V, in cubic centimeters is given by the equation V is equal to 4/3 pi r cubed, where r is the radius in centimeters and r is an element of the interval from 0 to 30. The surface area S in square centimeters is given by the equation S is equal to 4 pi r squared. Now for part A, we have, what type of polynomial function does each formula represent? Well, the first one is a cubic function, since we have a degree of 3. Then we have a quadratic function, since we have a power of 2. It says to sketch the graph of each function and state the domain and range. Well, in last chapter we learned how to apply transformations to it, so let's quickly do that. Again, this is not going to be a pretty graph, in no way am I saying you should create graphs like this on an actual test, but that's what I'm kind of stuck with doing, so sucks to look at a little bit, but I feel like it's better than showing you a rough version of my actual notes. So what did we have? We had 4/3. I'm just writing this pi r cubed. Or, well, it's V, so let's write V. First of all, you should always sketch the base graph. I'm not using units. You should definitely have units. So for example, if this is actually aligned, I would say this is 1, 1. And this is like 2. Therefore, we have to go all the way up to 8 somewhere over there. And so we have that. Make sure it passes through the origin, and then we'll copy the exact same thing over here. That's our base graph. Then we're applying these two constants, which are our A values. Pi is approximately 3.14, right? And so I would personally just multiply this by scale 4, just to make your life a little bit easier. Again, it's going to be a little bit bigger than 4. But now our V values should be, our V value should be times by a factor of 4. So our new graph is going to be stretched vertically. So from 1 we're going to 4, and from 8 we're going to like 32. And so we have like a really skinny graph now. 4. And that's what our graph will look like for part A. This is, V. And then for our surface area, we have another graph that we need to make. I guess I could have made them skinnier a little bit, but ooh, it's kind of cute. We have 4 pi r squared, right? Yep. Surface area is equal to 4 pi r squared. Parabola. Oh my god, that was a really shaky parabola. Parabola. Honestly, I feel like we're getting better. Again, this would be like 1, 1 over here. And this is 1, 1. Sorry. And then over here we have 2, 2. Let's pretend it's going over there. Now, again, we have 4 and times around 3, so it's around times 12. So from now, we're going all the way to like 12 for our y value, and then from 4 to 48. So again, we're just making it really, really, really skinny. Like, extremely skinny. That's around what our graphs will look like. Now, with this in mind, we had an R value restriction. So what we would actually do is select only the areas over here. right? But again, that doesn't change the fact that it became extremely, extremely skinny. Now, let's move on. Oh, sorry, the domain and range. Well, we know what the domain is. The domain is confined by our R values. Then, our Y values could be anywhere over here, which is greater than 0. And over here, it is also greater than 0. You could also, I'm pretty sure, find just the max and Y values by substituting R equals 30 into both of these equations. And so our range would be from that. However, I've seen similar questions to this, and they've just genuinely assumed that we're dealing with the base function. So they stated things like the domain is an element of all of real numbers, and also that y, for example, for the last one, for the quadratic, is that y is an element of all real numbers such that y is greater or equals to 0. Again, these sort of things you should definitely contact your teacher about and make sure you understand exactly what they're asking for, just so you don't lose marks for stupid mistakes. Now, part B. Determine the average rate of change of the surface area and the volume as the radius decreases from 30 centimeters to 25 centimeters and as it decreases from 25 centimeters to 20 centimeters. Okay, so for the volume, we could just make like 2 different graphs or 2 different sections for volume and surface area, but you'll be doing the exact same thing on both of them, so I don't really know why they have to make this question super long. Let's just zoom out a little bit. Okay, 30 to 25. So what we have is volume, just because it's the first one. And what points do we have? We have 30 and 25. So first of all, we're finding V of 30 is equals to 4/3 pi 30 cubed, which is equals to approximately 0.97.34, and then V of 25, that's a really bad 5, god, is equals to 4/3 pi of 25 cubed, which is equals to approximately 65,449.85. Lastly, I'd like to just combine them all into one question. I don't really feel like doing a B1 and B2. So I'll just split it up in just volume versus surface area. So then we have V of 20 is equals to 4/3 pi of 20 cubed is equals to approximately 33,410.32. There you go. Now we need to find AROC for when we're changing from 30 to 20. It's just for me to write it down. We would have 113,097.34 minus 65,449.85 all over 30 minus 25, which is equals to approximately 95 to 5 centimeters. I don't think you'd have to put the 0. I just wrote it because I thought it looked cute. Oh wait, centimeters squared, because that's the units we were working with. This would be centimeters cubed divided by centimeters, so centimeters squared. And then we have our second one, AROC, from 25 to 20. We had 65,449.85 minus 3,532 all over 25 minus 20, which is equals to approximately 637.91 centimeters squared. there you go. Those are our two answers for the volume portion. You have to do the exact same thing for the surface area. So we have S of 30. I don't want to write it out, the full thing. So I'm just gonna write what the value equals. It is around 11309.73. Then S of 25 is equals to 7853.98. Then we have S of 20 is equals to 5026.55. And those are our values. Again, this is what you should write out for your actual solutions on a test, but just because I'm trying to save us some time and not make this video forever, I'm trying to make it a little bit shorter. So IROC, sorry, not IROC, it's still IROC. AROC, just for the surface area from 30 to 25, is 1309.73. That's a bad 9. Minus 7853.98 all over 30 minus 25 is equals to 691.15 centimeters. Again, because it's centimeters squared, just a centimeters. So we take the degree of the centimeters off by 1. And then the last part, we again have AROC, but now from 25 to 20. And that is 7853.98 minus 5026.55 all over 25 minus 20, which is equals to approximately 565.49 centimeters. And that is part B. Oh, wait, we're supposed to describe any similarities and differences. Well, we see that as the volume was decreasing, the surface area was decreasing. That is about it. I don't really know what more they want from us, so I'll stick with just that. Now for C, determine the average rate of change of the surface area when the surface area decreases from this to that. Okay, well, they want us to find what values we have, at what radius we have these surface area values. So let's first of all do that. It's so satisfying to delete all of the work you did, but also kind of sad because you know you'll never get it back without rewriting it. But let's, oh, it's moving. Get back in there. There you go. So what we have is surface area of something is equals to 2827.43 centimeters squared. So what we could easily do is just solve the equation. So I don't know what I wrote it for. 2827.43 is equals to 4 pi r squared, which would mean that we just divide both sides by 4 pi. So let's do that. 2827.43 divided by 4. It's approximately 225 is equals to r squared, which would mean r is equals to plus minus 15. We know that it can be negative 15. Therefore, our answer is 15. Like positive 15. Then, for the other s value, we have s of r is equals to 1256.64. So 1256.64. Let's not forget the point. Is equals to 4 pi r squared. Again, we're going to divide both sides by 4 pi. 1, 2, 5, 6, 7, which is approximately 100, and this is equals to r squared. Again, r is equals to plus minus 10. We can't have a negative radius, therefore r is equals to 10. Now that we have these values, everything becomes extremely similar to our previous step, and that's just us finding delta y over delta x, which is equals to our y values 227.43 minus 1256.64 all over our x values, which is 15 minus 10, which is equals to 314.16 centimeters. And that is part C done. Part D, determine the average rate of change of the volume when the volume decreases from this to this. Again, it's the exact same question, just now we're dealing with the volume. It's a little bit difficult, well, at least a little bit more difficult to find the cube root of something, but with just some trial and error, I'm sure we could get this. I'm not gonna write that the volume bar is equals to this number because again, that's extra steps. You should probably write that on your test, but I'm not writing the test right now, so I think I'm good. Let's find for what values we have these. 1675.52 divided by 4/3, and then divided by pi. It's around 400. That's what I'm getting. If it's around 400, r cubed, let's try some values. 7 cubed, again, it's just a random number, 343. That's pretty close. 8 cubed is 712, so it's between 7 and another value, 7.5. That's 421, so a little bit too big. Then let's go in the middle. 7.25 times 7.25 times 7.25. A little bit too small. 7.3. A little bit too small. 7.4. It's a little bit too big, so it's around, I would just say, let's try the last one, 7.375. That's a tiny bit over, so I would just say r is equals to 7.37. That's just me guessing. Again, you could also write r is equals to the cube root of 400, and then you could just take, for example, is there a cube in there somewhere? I don't see a possible cube, but again, you could just have that as your r value. Then for the other one, best line I've ever done, we have 942.48 is equals to 4/3 pi r cubed, and this is equals to approximately 942.48. Did I write that right? Approximately 2.25 is equals to r cubed, so then r is equals to the cube root of 225, which is also let's just keep it at that. So then we have our AROC values is equals to our y values, which is 75.52 minus 942.48 all over x, or our r values, which is square root of 400 minus cube root out of 225. Type this into your calculator and you should get approximately 570.07 centimeters squared. So that's our final answer. Now it says to interpret your answers from part C and part D. Well, from what we've seen is that as the values continue to decrease, like the R values continue to decrease, so did the average rate of change for both the volume. Oh wait, no, for the volume, it continued to decrease all the time. Is that right? Yeah, that seems right. And then for the surface area, it also was decreasing on every step of the way. So what I would say is that as the always, as it decreases, both of the value decreases. Also, from previous answers that I've seen, people have been saying that you could just describe what you found in the previous questions. Well, of course, what we found out is that is when the surface area was decreasing from this value to that value, we had an approximate rate of change of 314.16 centimeters when the radius was decreased from 15 to 10, and also the snowball was decreasing in volume for part D from the value of cube root of 400 and cube root of 225 by a rate of approximately 570.07 centimeters squared. That's what you could say for this question. Lastly, we have question 10. So for question 10, we have another similar question. As water drains out of a 2,000 liter hot tub, the amount of water remaining in the tub can be modeled by the following function, where T is the time in minutes, and dot is its constraints, and the volume of T is the volume of water in liters remaining in the tub at the time T. For A, we need to determine the average rate of change of the volume of water during the entire 100 minutes, the first 30 minutes, and the last 30 minutes. So let's do that quickly. Again, oh, this became really small. Sorry about that. Let's zoom me back in. Excuse me. That's our final equation sort of ordeal that we have. What I like to do for these kind of questions is just use the full equation to solve it. So for question 10, we have A at full 100 minutes. So if we substitute 0 into the equation, so yeah, the volume at 0 is equal to 2,000. Sorry, I didn't look at it the right way. And then the volume at 100 is actually 0. So now let's do the AROC. So delta y over delta x is equals to our y values minus 0 over 0 minus 100, which is equal to negative 20 liters per minute. Again, this was in liters, this was in minutes, that's why we're getting these units. Now for part 1. For part 2, we have to find V of 30 now, which is equals to approximately 480.2. So then again, our AROC values would be 480.2 minus 2,000 all over 30 minus 0, which is equals to negative 50.66 liters per minute. As we have part 3, and that's V of the last 30 minutes, which would be V of 70, which is equals to approximately 16.2. And then instead of using our 0, we need to use the b of 100. So let's do that. AROC is equals to 0 minus 16.2 over 100 minus 70, which is equals to negative 0.54 meters per minute. So from what we see here, actually that might be part B. Let's actually read what it says. Part B, what do the values from part A tell you about the rate at which water drains from the tub? Well, we could see that it's not quite linear. It's not at a constant rate of change, you know? So from here we had negative 20, and then it grew, or I guess decreased further, into negative 50.66 liters per minute. However, as we kept going, it appeared at one point we started to actually go back up to the point where we were draining just a tiny bit of water left per minute. Oof, let's put you back in here. Again, you could try to graph it and find the equation of it, but describing it should be good enough for this. Now, I think, yeah, part D is to sketch the function of the graph. Let's quickly get into Desmos and do that. Okay, so this is what the function actually looks like when it's graphed. And if on your drawing it wants us to sketch the secant to respond to the time intervals in part A. Well, what we know is that we have the secants should just be the line segment that intersect the graph in two parts. So y is equal to mx plus b. There we go. Now, what did we have? We found out that the AROC value, which is actually the slope of the secant, for the first part was negative 20. Now we just need to find the b value, and honestly, you can see these are not anywhere near enough, but this is what we know for sure, since we have our y value is equals to 2000. So that is our first slope. Let's keep it there. Now, let's find the second one for the first 30 minutes. So for the first 30 minutes, we said that the AROC was 50.66 liters per minute. If this intersects at 30, we're good. There you go. That's our second slope. And lastly, we need our last 30 seconds, 30 minutes slope, which was 0.54. 0.54. That doesn't seem quite right. So let's figure out what we need to do here. Oh, well, because it's the last 30 seconds, this should be around, we should be gone up. I'm trying to figure out how we're supposed to make this fit into the equals to 0. Of course, we could just start by doing reverse. So 100, 0 is equals to negative 0.54 of 100 plus b. Then we have this is equals to 54. So 54 is actually equals to b. So let's do that. 54. Did we get this right? And that's 70. There you go. That is our final secant line. So I hope you understood how we do this. This is grade 9 knowledge, so hopefully you remember some of it. Now we're done with the AROC portion. Let's move on to the IROC part of the textbook. Okay, so for IROC, I assigned question 2. At each of the indicated points at the graph, is the instantaneous rate of change positive, negative, or 0? Explain. Okay, well, this is rather simple. So for A, it is definitely positive because the slope of the line is positive and it's going up. For part B, it is 0 because it is a horizontal line, so its slope is 0. Then for C, it is negative because it is going down. It's a downward line. B, estimate the instantaneous rate of change for points A and C. Okay, well, as I said, what we need to do is have a point very similar to the actual graph. So for part A, or for point A, we definitely know that A is 212, and then another point really close to it is 1,8. So then we use those two values, and we would get that the slope of the line is equals to 8 minus 12 over 102, which is equals to 4 meters per second. For point C, we do that exact same thing. C, we know, is the point 7 and 7. Then, sorry, I had to yawn. Then we have the points, let's say 6 and 13 is a good one. Again, we find the slope of the line by using those 2 points. So we get things like 7 minus 13 over 7 minus 6, which is equals to negative 6 meters per second. Now it's asking us to interpret the values from part B for the situation presented in the graph. Well, what we have is actually the height in meters and the time, which would actually represent the velocity of the tennis ball over at that particular instant. Now for question 4. Use 2 different methods to estimate the slope of the tangent at the point indicated on the graph. Well, we have the point 2.5 and approximately I would say 32, 31. What we could do is, of course, use that point itself, which would be point 1. Then we could use another point on this orange line to find the second value. So for example, anything that x checks the square, for example, 4 seems to be very close to 70. So what I would do is I would use these 2 points and then find the slope. So we would have 70 minus 31, or 32, all divided by 4 minus 2.5. And that would get us our slope, which is around 25 meters per second. Then we could have another point on the same graph, on the same point. So for example, the point 220 seems extremely promising. And then you perform that exact procedure. And once again, you will get approximately 25 meters per second. What's more? Again, these values should all be the same value because we have a straight line and we're searching for its slope. Now let's move on to question 6. The table shows the Consumer Price Index, CPI, every 5 years from 1955 to 2005. Determine the average rate of change, the CPI, from 1955 to 2005. Again, this is rather simple. We just did this. Just use the delta y over delta x equation and you will get the following values. You would do 127.3 minus 16.8, all divided by 2005 minus 1955, which is approximately 2.21 CPI per year. Then for part B, it wants us to estimate the instantaneous rate of change in the CPI for 1965, for 1985, and 2000. Well, what we have to do here, is since we have a table, is actually use the values beneath it and the values in front of it. So 1965, we have to use 1960 and 1970. So from 1965 to 1960, we would do 220 minus 18.5 divided by 5. And then from here, we would do from 1970 to 1965, we would do 24.2 minus 20, all divided by 5. That will get us a range of numbers between for what the CPI for that year actually was. So for 1965, that range would be between 0.3 from 1960 to 1965, that's the value, and between 0.84, which was from 1970 to 1965. We will follow the same procedure for 1985 and 2000. Again, I feel like this is extremely repetitive, so I'm not going to show you that exact part. Lastly, or not lastly, but C, compare the values found in Part A and Part B. Explain any similarities or differences. Well, we have, so for here we got 22.21. Then for here we got range of numbers. So for 1985, if you did the work, it should be between 366 and 452. And from 2000, it should be around 1.86 to 2.76. So actually, over here, these two values are actually way larger than the average we got overall. And when you consider all three of them, they're way larger. Well, they are larger than the value we got in Part A. And I guess that's it for that question. Now we have question 8. On Earth, the height h in meters of a free-falling object after t seconds can be modeled by the function as follows. While on Venus, the height can be modeled by the following function, where t is greater or equal to 0, and k is the height in meters from which the object is dropped. Suppose a rock is dropped from a height of 60 meters on each planet. Determine the average rate of change for the height of the rock in the first 3 seconds it is dropped. So here we have our final way of determining AROC and or IROC, and that is using the equation. So here on Earth, we would use the values 0 and then 3 to substitute into the Earth equation, and then we would divide it, or we would find the difference in delta y over delta x, and that would give us approximately negative 14.7 meters per second. Again, this whole chapter is extremely repetitive. You just need to remember the formula delta y over delta x and how to analyze it using various instances. For example, for AROC, you need 2 points. For IROC, you need a very close point if it is a equation like we have here. So for B, when it's asking us to find the instantaneous rate of change, we could finally use that portion. So let's do that. So let's delete this. I don't know where those stay. Please be gone. Thank you. So what we have is here. We have, oh, I scrolled over. H of t on Earth is equal to 4.9 t squared plus k, where that is the height. We don't really, the height is 60, so h of t is equal to negative 4.9 t squared plus 60. This is Earth. So on Earth, the instantaneous rate of change would be actually at 3 seconds. We would use, first of all, the value of 3, and then add a very tiny interval to it, for example 0.1, and then square it, plus 60. This is our first part of, this is our y2 value. Then we minus our y1 value, so negative 4.9, and then actual t value squared plus 60. And over here, this is our t values, t T2 and T1. So T2 is actually 3.01 and this is minus 3. This would give us an approximate number of negative 2.945. That is around what it would be. Now, you could keep going like this until you get a very close number. So for example, instead of using 0, 1, we could have used 0, 0, 1, or 0, 0, 1, or 0, 0, 0, 1. So the one that I like to use is 3 zeros. It's a little bit difficult to fit. There you go. If we use 3 zeros, then we would actually get the value of 29.4005. As you can see, our values are getting very close to the value of 2.94. Sorry, negative 2.94. That is the instantaneous rate of change. So what we're kind of doing is we're bringing the second point of the secant so close that you cannot even tell that it is actually different from the point that we had originally. That is how we're currently determining the IROC for certain situations. And that is why, and that is how we're going to be doing it for the rest of the year, or the rest of the semester. On Venus, we do the exact same thing. We just have h of t is equals to negative 4.45 t squared plus k, which is equals to h of t, which is h of t is equals to negative 4.45 t squared plus 60. Again, I like to substitute in 3 zeros, so that's what I'm gonna do. So Venus is equals to, Venus is negative 4.45 and the 3 followed by 3 zeros, 1 squared plus 60. This is what y2 minus 4.45 and then 3 followed. And then 3 plus 60, I forgot the squared, all over 3.0001 minus 3. This gives us a value of approximately negative to 6.7 meters per second on Venus. And this is also meters per second on Earth. What I would do and what I would recommend is actually going through all the different values. So use 3.001, 3.01, and maybe like 2.99 to find to what point those values are converging to. That is the most efficient, well, it's not really efficient, but that's the most thorough way you could determine the IROC and not make any mistakes. It's also going to show your teachers that you actually understand the concept. Again, I'd recommend listening to your teacher and them explaining to you exactly what they want for these types of questions, how many different values they want you to test, and then find the converging value. So pay attention to that more than what I'm teaching you right now. Now for part C, it says to interpret the values in part A and part B for the situation. Well, I know this is going to be a shock, but it appears as though a rock on Earth actually falls faster than a rock on Venus. Since, as you can see here, the Venus one has a smaller value than the Earth one. And that's all we're going to say. Lastly, we have, we also have 9 and 11. I thought we only had 9. So, for 9, the manufacturer estimates that the cost, C, in dollars by producing X MP3 players can be modeled by the following function. Determine the average rate of change in the cost of producing from 100 to 200. So again, just substitute 100 and 200, find those C values, divide delta Y over delta X, and that's about it. For B, estimate the instantaneous rate of change of the cost producing 200 MP3 players. As I said, please use variance numbers. It doesn't quite make sense to me to use decimals in this situation, but you'll have to. So you'll have to pretend as though there's a 1/10 of an MP3 player that you're selling, or like a 1/100th. But that again will let you have a much more realistic estimate of what the instantaneous rate of change is. Lastly, we have to interpret those, so just compare if it is what those values mean. So for example, if you got that producing between 100 to 200 is like much higher in cost, so the average rate of change is higher than the instantaneous rate of change of 200, then you would say it's more beneficial to make more than 200, make exactly 200 MP3 players. If it's the opposite, then state the opposite. Also, does the cost ever decrease? So actually we could determine that by simply looking at the equation. We see there's no negatives here, and we have a cubic. We can't have negative MP3 players. Therefore, our x values is always going to be greater than 0, or equal to 0. If it is greater or equal to 0, we're always going to get a positive number times a positive number plus a positive number, which would always mean we are increasing. Therefore, no, we never decrease. Lastly, we have question 11. A worldwide distributor of basketballs determined that the yearly profit P in thousands of dollars earned on the sale of X thousands of basketballs can be modeled by the following function, where X is between 0 and 25. Determine the average rate of change. So what you need to remember is that we said that the X is in thousands of basketballs, and here we have 2,000 and 6,000, so do not substitute 2,000 and 6,000, substitute in 2 and 6. The same thing goes for this one. And then again, you're just going to substitute those values in, find P1, P2, X1, X2, and then find delta of Px over delta of X. What conclusions can you make about comparing the values in part B? Again, just compare whether or not this one is bigger in cost or bigger in profit, if this one is bigger in profit, and just state what you see. C, estimate the instantaneous rate of change. Again, you could use, for example, I'd recommend using like hundredths of a basketball, because again, these values are in thousands. So if you use 1,000th, that means you're actually just calculating one basketball. So do that. Don't go any further than 1,000th, and that should give you your a really good estimate for the instantaneous rate of change. Again, just compare those values for part D. Now for part E, it says to graph the function, which I'll quickly do. Hopefully you have paused the video to actually do all the work yourself by now. I'm not going to do it because it feels so repetitive to show the exact same steps over and over again. If by now you don't understand what you're doing, please just message me and we'll help you out. The question disappeared. But I don't really know what else to tell you besides, yeah, please reach out to me and I will love to help you. Is equals to negative 0.09 x to the power of 3 plus 8.9 x to the power of 2 plus 9x. There we go. Oh, x is big here. So this is our function. Also, if you didn't know this, you could actually do a range for what your what you want decimals to actually show you. So we want to go to 25. And this is our little function over here. It's kind of cute. There you go. So how does the graph support your answers to part A and part C? So it wants us to find the average rate of change from 2 to 6. So y is equals to mx plus b. B value, well, first of all, we see that it's increasing, and then we need to get it all the way to 2. So I'm just gonna x equals 2. X equals 2. I really can't. Let's change the color of it. Just so we can tell what's going on. Doesn't seem... Does this intersect you once? No, it doesn't. So you're gonna just mess around with this value a little bit. You know? Maybe just move it up and down. Although 10 does look nice. Maybe like 100. Oh my god. Sorry. I'm just got deleted. 100. Doesn't look like it. 55. Doesn't look like it. Of course, you could just do the way I told you it. This is what the graph looks like. We could see that it's going to be increasing rapidly over here. Then it's going to slow down. Then it's slowing down like over here. It's still a little bit slow. And then it goes straight down into a thing. That's about it for this question. Again, if need really be, I will redo this all full question by writing it out, but I don't really see the need. Again, you're just going to be substituting, let's say 2. Honestly, let's do that here so I don't have to write it out. Substitute 2 in to everything. It's our part y2 value. y2. Then we do the exact same thing for 6. So then delta y over delta 6 is equals to 0.6 minus 24.84 all divided by 6 minus 2. And that's our answer, 19.44. If that's not what you got, please try again. That's all I could say. Also, if it's 19.44 and this is in thousands, we have to multiply this by 1,000. So we actually have 19,440 as our final answer. We're gonna do the exact same thing for part 2 of A. So let's do that. Honestly, I'm just gonna quickly 16, sorry. 16, and then 16, then 20. Oh, it might have been easier to just add a 0. Damn. Again, we're just gonna, this is 216, and this is 259.2. Make sure your numbers actually stay consistent. So at first of all, I enter 20, and then minus 16, negative 10.8. So actually, if we sold between that many, our profit is actually negative. Which means you wouldn't want to buy or sell that many basketballs. Because you're not making any money. That is kind of the fun part. Next. For C, instantaneous rate of change for 5,000. 5,000. Really easy. First of all, substitute 5. Then we could do 5.01. Then 5.001. That's person the one I'm gonna stick with. Actually, you could do it even more. But as I said, this is in thousands, so we should be fine. We actually have 81 minus 81.02511505399. Your calculators won't be as precise as these ones, so it's not like it matters, but there you go. It's around 21 times 1,000. We would get around $21,150. And then the same thing we're gonna do for 18. I think you get it by now. For 18, the answer would actually be negative 10,440. So again, it's more beneficial to make around 5,000 basketballs, because if you make 18,000, you're just gonna lose your money. So yeah, again, that's all I'm gonna say here. This graph shows this rather well. As you can see, we're increasing all the way until 16. After 16, they're just starting to lose money. They're just not making any money anymore. And that's the sad part. So thank you for coming today. And that's about it. Again, thank you so much for listening to this lesson. I think it's going to be the longest one we had so far, just because I'm combining 2 chapters into one. with all of the homework we did today. However, we did finally finish polynomial functions, so you're officially done 1/8 of the advanced functions course, so congratulations. I will try to make the chapter 2 slides very soon, and so the chapter 2 videos should be coming in around a week. I hope you're having a wonderful time learning, and thank you so much for listening. Goodbye!